Okay, so having classified differential equations, next we see what we mean by solutions of differential equations. And we are also going to discuss a little bit about the nature of these solutions. Let's see the definition first. Consider the following nth order ordinary differential equation. We will henceforth write ODE in place of an ordinary differential equation. Let me write the equation there. dny dxn equal to 0. Let us also call it 1, where f is a real function of its n plus 2 arguments. Although it's it's clear what this equation means, but still, let us make it even more clear. I am going to inject some explanations which are not parts of the definition, and they will appear between dashed lines like this. What is f? F is actually a function which looks like this. It's a real function means what? It's a real valued function. The outputs are real and the inputs are coming from some set D, and that D is a subset of the Euclidean space R n plus 2. To put things simply, f is a function whose input is a vector having n plus 2 real number components and output is a scalar or a real number. That's what f is. Originally, f has nothing to do with derivatives or anything. F is just a function. Or to put it even more simply, f is a function, or to put it in another way, you can look at f in another way. F is a function of n plus 2 real variables and takes on real numbers as outputs. Okay. And we are simply using this function f to express the differential equation in the most general form. Now, number 1, we call a function. Now we are going to define two types of solutions of that differential equation 1. The first type is called an explicit solution, which we are defining. We call a function f from I into R, where I is an interval in R an explicit solution of 1 if the nth derivative of f exists for all x belonging to I. Note that this requirement also means that the lower order derivatives also exist at every input coming from I, such that this Fnx is defined for all x belonging to I, such that what does it mean that this is defined? It means that say you choose some x from I, then that x gives you x is one real number, f of x is another real number, the derivative of f at x is another real number. Like that you get n plus 2 real numbers. These n plus 2 real numbers give you an n plus 2 vector, or a vector with n plus 2 real components. That vector should belong to the domain of the function f. That's what we mean when we say this is defined, that this makes sense, it has a well defined meaning, and it is equal to 0. Okay, if this happens for all, we need to also write for all x belonging to I. If all these conditions are true for all x belonging to I, then we call such a function an explicit solution of our differential equation on the interval I. Let us keep the differential equation as long as we have the definition, because it's not over yet. For all x belonging to I. So that's the meaning of an explicit solution. But there is another type of solution as well. A relation g of x comma y equal to 0 is called an implicit solution of our differential equation 1 if it defines means this relation defines at least one function f from I to R, where I is an interval in R. That is an explicit solution of 1 on I. Oh, do not confuse between this one and this I. Okay, it's understood what this means and what this means. So instead of getting a An explicit. Explicit means you say something explicitly if you say everything about it, clearly, directly. Implicit means something is hidden. Okay, so if this relation defines at least one function, a relation may define more than one function. We are going to see one example of that. Such that that function is an explicit solution of our differential equation on its domain, which is an interval, then we will call this an implicit solution of our differential equation. And then there is a third point about this definition as well. Both explicit and implicit solutions will be called just solutions, simply solutions. Okay, so that is the meaning of solutions. Now let's see two examples where these things will become even more clear. And we are going to follow every little detail that the definition has in these examples as much as possible. So this is example 7. The example begins with a statement. The statement is this, which is a claim. The function y equal to what is the function 2 sin x plus 3 cos x is an explicit solution of the differential equation this on R. And now we have to show how. We have to understand how this is true. This is our differential equation, and we are saying that this function is an explicit solution of this differential equation on the interval R itself is also of course one interval, open interval minus infinity comma infinity. Okay. So let us see one by one if we really are following the definition. First we have the differential equation. Is it an ordinary differential equation? Yes. It's a second order ordinary differential equation. Alright. So what is that function capital F in this case? That function is a function from R4 to R. And the definition of that function is this. x2 plus x4. This is the legitimate function on R4. You take any 4 vector, what is the output? The output is the sum of the second component and fourth component. Note that as I remarked there when writing the definition, that this f actually has nothing to do with derivatives or anything. We can just use this function f to express the differential equation. So you can clearly see that if you do so, are you really getting our differential equation? What is this? What is f of x, y, dy dx and d squared y dx squared equal to 0. This is true if and only if the sum of the second and fourth component. Yes. Okay, next we come to the function. The function is not given as f of something, but it's given in this notation that y is the dependent variable. But of course, our function more formally looks like this. That means the I interval for our function is r. Here I is equal to r. And what is the definition of the function? Fx is 2 sin x plus 3 cos x. Okay. Then what do we need from f? That it should have derivatives up to the second order. Yes, that is true. Why? Because sin x and cos x are themselves differentiable functions on the entire real number system, on the set of real numbers entirely. And you can differentiate them as many times as you want. So their linear combination is also going to be differentiable. So these are simple results from calculus. In fact, the first derivative at any real number x is 2 cos x. If you differentiate sin x, you get cos x. Differentiating cos x, you get minus sin x. And you can differentiate once more. Minus 2 sin x minus 3 cos x. So you can clearly see that you are getting minus f of x, which means that the sum of f of x and its second derivative is equal to 0. That is, we have this. And this is true for every real number x. At every real number, you calculate the second derivative and add it to the value of the function at that real number, you are going to get 0. And that's how this function is an explicit solution of our differential equation on the entire real number system. And if you really want to see some more details, for example, for each x, if you take this vector which is a vector in R4, is this meaningful? The sum of f of x and f double prime of x, is it meaningful? Yes, of course it's meaningful. It's just this sum. And not only is this meaningful, this is also equal to 0. And that is why everything from the definition has been followed. So this is really an explicit solution of our differential equation. Okay. Next, let us see another example. In this example, instead of having an explicit solution, a relation is given. Again, this also starts with a statement or a claim. The relation x square plus y square minus 25 equal to 0 is an implicit solution of this differential equation. It's a first order differential equation, x plus y dy dx equal to 0 on the interval. This time we are not saying the entire R. On the interval I equal to minus 5, 5. Okay, there is a reason for choosing this interval, will become clear. How? See, according to the definition, using this relation, you should be able to get at least one function on this interval which should be an explicit solution of this differential equation. If you want to get a function of x from this relation, what do? You solve for y in terms of x. So, if you take the equation, and of course you can transfer the minus 25 to that side, and this gives you y squared equal to 25 minus x squared. And in fact, this is why you need your x to lie in this interval. Why? Because if x lies in this interval, then the absolute value of x is less than 5. So the square of x is less than 25. And that's why 25 minus x square is positive. We want that because the left hand side is, well, not exactly positive but non-negative. Why we need open interval here and why we cannot take closed interval, that will also become clear very soon. But anyway, so if you now fully solve for y, you are actually getting two possible values of y for a single value of x. In other words, this relation does not exactly define only one function of x, but rather it defines two functions of x at once, and both the functions have this interval as their actually this interval. But for some reason we have to choose open interval, and that reason will now become clear. And the reason is that at the boundary points, if we include minus 5 and 5, the derivative does not exist. You cannot differentiate any of these two functions. So what are the explicit functions we are getting from this situation? We are getting two functions, in fact, not just one. And the functions are these. f1, let's call one of them f1, and the other one is f2. f1 of x is the positive square root of 25 minus x square, and f2 of x is the negative square root of 25 minus x square. Actually, you know what these functions are. You also know how the graph of this equation looks. It is a circle. Now the circle itself cannot be the graph of a single function because it fails the vertical line test. Why? Because if you draw the circle, which of course would be centered at the origin and will have radius 5, then some vertical lines intersect the circle at more than one point. Some of course do not intersect it at all. So instead of defining one function, it defines these two functions. This function has the upper portion as its graph, and this f2 has the lower portion of the graph. Okay. Alright. Now for any x in I in our open interval, let us differentiate the first function at x. That means let us calculate this using the differentiation rules you know from school. So it gives you 1 divided by, you have to use the chain rule, right? And the other differentiation formula. So because you have square root, first if you differentiate this with respect to 25 minus x square, you get 1 divided by 2 times square root of that. And then you multiply that with the derivative of 25 minus x square with respect to x, that is the chain rule. That gives you minus 2x. So what are we getting from this? After cancelling 2, you can see that f1 prime of x is minus x divided by f1 of x, because this is just f1 of x. Do you now see why we cannot take minus 5 or 5 in place of x? Because then the denominator becomes 0. Why is that so geometrically? Geometrically, what is the derivative? The tangent of the slope to the curve at the point where you are differentiating. Oh, I said tangent of the slope, sorry. Slope of the tangent, yeah. So, if you calculate the derivative, say here, then this is your tangent, fine, it has a slope. But at minus 5 or 5, at x equal to 5 or minus 5, the tangents are vertical. So, slope is undefined. That is why we cannot take minus 5 and 5. When solving the equation to find these two functions, you can take minus 5 and 5. But if you want to differentiate, you cannot take. Okay. So now from these things, what do we get? You see that ultimately after doing rearrangements and everything, you get x plus f1 of x times f1 prime of x is equal to 0. Isn't that the equation actually? X plus y dy dx equal to 0. X plus y dy dx equal to 0. So yes, f1 really is an explicit solution of our differential equation on this interval. What about f2? Let us see that also. f2 prime of x again is coming from our I. So if we differentiate this, we will get almost exactly what we got there, but with a minus sign. That means already you are getting a minus here. So this time you will get this. However, f2 is minus of this. That means this is x divided by minus f2 of x. Again you are getting that same form. And so in this case also you get this. So you have actually got two explicit solutions. Only existence of one is enough to declare the original relation x square plus y square equal to 25 an implicit solution. But we have anyway got two. Okay, so that's an implicit solution. However, is any relation like that going to be an implicit solution? Let us take another relation for the same differential equation. This relation, say, plus 25 equal to 0. That was a different one, x square plus y square minus 25 equal to 0. Now you of course know from calculus that to to find dy dx from such an equation, there is no need to really first of all find y as a function of x and then differentiate. You can do implicit differentiation, which is simply differentiate both sides with respect to x and treating y as a differentiable function of x and using chain rule. So if you do that to this relation, differentiating x square of course gets you 2x, and using the chain rule, differentiating y square gives you 2y dy dx, and of course plus 0 equal to 0. Okay. So, and then if you, 0 of course will vanish, and if you divide both sides by 2, you are getting x plus y dy dx equal to 0. That is actually our differential equation. So, should we call this also an implicit solution like the other one? No, we cannot say so. Simply solving the differential equation in this sense formally is not enough for a relation like this to be an implicit solution. Remember the definition, an implicit solution should not only solve the differential equation but should actually be able to define at least one function, a concrete function which is an explicit solution. Can we define a function from this relation, a function of x? No, we cannot define. Let's see the reason. Well, one reason is of course that there are no x and y values that satisfy this equation. Why? That's because x square and y square are both non-negative. They are never negative. So how can you get 0? Already you have 25 here. In order for this to be 0, x square plus y square has to be minus 25, which is not possible if x and y are real numbers. Another way of looking at it is this. Say without thinking of those things, you just blindly solve for y, like how we did there. You then end up getting this. Again, the expression under the radical sign cannot be made even 0. Forget about making it positive, it cannot be made even 0. Again, because x squared is non-negative, x square is non-negative, but minus 25 is negative. So no, this doesn't give you any real function at all. And that is why, in spite of formally satisfying the differential equation, this is not an implicit solution. Relations like this which formally satisfy the differential equation. What do we mean by this word formally actually? It just means that something has the form of a solution. It has the appearance of a solution, but it's not the real thing. It's like an imposter. It's trying to be a solution, it's disguising itself, but in the end, if you scrutinize it minutely, you find that no, it's actually not a solution. However, when we learn the methods for solving different types of differential equations, there are types of differential equations and there are special methods for finding solutions of those equations. What we do there, we search for formal expressions or formal relations, not expressions, but formal relations like this, which formally satisfy a differential equation. But why? That's because our main aim would be to familiarize ourselves with the methods, and then when you further investigate those formal solutions, this type of things are called formal solutions. To see if they really are implicit solutions, then the entire truth will be revealed. So at first, in the beginning, we won't really be too much concerned about seeing if we are really getting an implicit solution. We will be happy and content with formal solutions for some time in the beginning. But then when we become more serious, and by that time we will have become accustomed with the methods of solving special types of differential equations, then we will take those formal solutions and then further investigate to see, okay, so this is an implicit solution, that is not. Okay, so those parts we will do afterwards. It is something like the difference between calculus and real analysis. In calculus, the theoretical, the why questions are really not answered. The main aim is to teach you how to differentiate and integrate functions, how to apply differentiation and integration to solve some problems elsewhere. And then when one has enough practice with those things, then one goes and asks, okay, so I know, for example, L'Hopital's rule, I have been using it for such a long time. I know integration by parts, I know some other things also, I know the fundamental theorem of calculus, things like that. Okay, but why are they true? That's when you go for answering those why questions, then analysis starts. So the situation is somewhat like that right now. We will learn the methods by finding formal solutions first. Whether the formal solutions are actual solutions, that we will see afterwards. Yeah, that's what the author says. So we have come across three types of solutions. An explicit solution where you see the function in its entirety, which really solves the differential equation in the sense given in the definition. Number two, an implicit solution which has at least one explicit solution hidden inside it. And number three, formal solutions, some of which really are not solutions, but when we find these solutions, some of them may be solutions. Okay. So with this, let us just end the video here itself, and in the next video we will see what we have after this, and slowly we will go towards the special types of differential equations for which there are special methods for finding solutions. And again, I am saying that we won't right off the bat, we won't really find explicit solutions, okay, this is the solution or these are all the solutions of the differential equation. We will just learn the method by finding formal solution. Did you notice one more thing? For the first differential equation, that second order equation, we gave one explicit solution. For the second differential equation, which is our first order equation, I think it was this one, x plus y dy dx, that implicit relation gave us two different solutions. This raises another question. What are all the solutions? Okay, we will see all these things. So that's it for tonight, and tomorrow what do we have? Oh, trigonometry again. Okay, so see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Group. Have a nice night.